Hello everyone, I am Soumyarup Hait, a PhD scholar under the supervision of Professor Sujit Chaudhary at Indian Institute of Technology, Delhi. So before starting my presentation, I would like to thank Professor P.K. Mudli for giving me the opportunity to present my work here and also congratulate him for his successful 10 years at IIT Delhi. So my work is entitled The Interlayer-induced enhancement in spin pumping efficiency in beta tungsten CO2 fuel heterostructures. So the outline of my presentation is as follows. First, I will introduce the concept of spintronic memories, which is already introduced by Professor Rahul Mishra. And then I will discuss about my materials and the motivation behind this work, followed by the result and discussion and conclusion. So if you see the memory hierarchy, current memory hierarchy of the conventional memory device, the two things that bothers is the volatile nature of the core memories and the speed gap between them. So a spintronic based memory such as a magnetoresistive random access memory or MRAM being a non-volatile and fast memory can replace them. And as also mentioned by Professor Mishra, that there are several promising kind of spintronic memories are there, such as spin transfer torque based memory or STT-MRAM and SOT-MRAM, and there are some issues in STT-MRAM like low endurance, and there is a possibility of time dependent MTJ breakdown. Hence, a promising memory is SOT based MRAM. What in SOT based MRAM, what happens when we apply a charge current in a non-magnetic material of high SOC strength, spin current can be generated through spin Hall effect, and that travels to the magnetic layer and switches the magnetization. Now, what is important in this aspect is that the non-magnetic layer should have very high SOC strength, and also the interface quality is very crucial as the spin current will be traversed through that interface. So examining the interface quality is very crucial. Now, in this regard, spin pumping is a very easy and widely accepted method of examining the interface quality in such ferromagnetic non-magnetic heterostructure, where a spin current is generated in a ferromagnet due to ferromagnetic resonance induced magnetic precision, and that travels to the non-magnetic layer, which results in enhancement in the damping constant. Now, in my research, I have opted a very exotic class of ferromagnetic material, a full usual alloy, CO2 FeL, which is half metallic in nature and which results in very low damping constant and very high spin polarization. And as a non-magnet, I have opted for the beta phase of tungsten, which reported to provide very high SOC strength, results in very high spin Hall angle. So the first motivation of this presentation is to study the spin pumping phenomena in beta tungsten CFA heterostructure. And after then, our motivation was to tune this spin pumping through using different interlayer. Now, there are reports in which people have used different interlayer in mainly PT-based ferromagnet heavy metal heterostructure, and then they show using interlayer they have basically enhanced the SOT efficiency. But in all these reports, the main objective was to make the interface more spin transparent through this interlayer rather than taking any additional contribution from the interlayer. However, in our study, we have opted for 4 different interlayers, 2 of low SOC strength and 2 of high SOC strength. And also we have varied their thickness just to observe the effect of this interlayer on the spin pumping efficiency. So for that, we have grown 8 different series of samples. Few series of samples are grown. Are grown just to study the spin pumping phenomena in tungsten CFA heterostructures. And after that, 4 different series are grown where in between a 6 nanometer tungsten and 8 nanometer CFA, interlayer of different SOC strength and also different thickness are grown. All the samples are grown at room temperature using ion beam sputtering technique. So before going into the spin pumping or spin dynamic measurements, we have tried to see the structural quality of our grown structures, and the Granting incident XRD diffraction suggests that or the grown tungsten layer are of beta phase, and the CFA layer is of A2 disordering. And also to reconfirm the beta phase of the tungsten, we have performed the resistivity measurement of single layer tungsten thin films, and the resistivity value is found to be in the order of 200 to 165 microohm centimeter, which matches with the reported resistivity value of beta tungsten. After that, to understand the quality of the interface of the grown heterostructure, we have performed XRR measurements on a few selected samples of each of the series, and we have seen that the interface quality is quite good, or I can say very smooth, with interface roughness less than 0.5 nanometer, and the thickness of each layer also mimic the nominal values. To reconfirm or reestablish the smooth quality of our heterostructure, and also to identify the chemically identify the different layer, we have also performed secondary ion mass spectroscopy on a few selected sample involving the interlayers, and we see that the tungsten interlayer or CFA interlayer surface are very smooth. So after establishing the structural quality of our grown structures, we have also performed spin pumping analysis in tungsten CFA heterostructure. First, we have performed the ferromagnetic resonance measurement on a series where the CFA thickness was fixed at 8 nanometer, and the tungsten thickness is varied from 0 to 10 nanometer. And this variation are analyzed using a ballistic model, and using this, we have initially seen that with a tungsten layer of 4 nanometer or greater, there is almost a 50% enhancement in effective damping constant. And fitting this with this ballistic model, we have tried to got the spin mixing conductance and of the constant interface and spin diffusion length of beta tungsten. The spin mixing conductance is found to be 13.17 nanometer to the minus 2, and spin diffusion length of beta is found to be 2.12 nanometer. However, it should be noted that this model does consider the spin backflow from the tungsten layer through this exponential term, but it do not consider the spin backflow from any surface of the CFA layer. And to account for this, and this is why this spin mixing conductance is called the intrinsic spin mixing conductance, not the effective one. And to account for this, we have also performed CFA thickness dependent spin pumping measurement, where the tungsten thickness was fixed at 6 nanometer and the CFA thickness is varied. And to take account the finite size effect induced surface interface scattering, we have also performed this measurement on a single layer CFA thin films with different thicknesses. And fitting this variation with this model, we have calculated the effective spin mixing conductance, which is found to be 6.51 nanometer to the minus 2. And using the value of this, we have also calculated the transparency of the concerned interface, which is found to be almost 60%, which is larger than the previous reports. Now, after establishing the spin pumping phenomena in tungsten CFA heterostructures, next we observe the effect of different interlayers of different SOC strength and in different thickness of interlayer on the spin pumping efficiency. So we see that for the interlayer with low SOC strength, that is aluminum and magnesium, the spin pumping is blocked for any thickness of the interlayer. This is expected as the low SOC strength of the interlayer block the spin pumping from the CFA layer to the tungsten layer. However, for the interlayer with high SOC strength, very interesting phenomenon occurs when we see that the damping constant is first found to increase with interlayer thickness and then reduces with further increment in the interlayer thickness, and finally with for a higher interlayer thickness, it is saturated at a particular value. We have observed for 2 nanometer interlayer of both molybdenum and tantalum, we have observed damping constant value which is higher than even for the tungsten CFA heterostructure. and this is accredited to the combined contribution from the interlayer as well as the tungsten layer. This phenomena can be understood through the two parameters. One is the SOC strength of the interlayer and also the spin diffusion length of the interlayer. In general, the spin diffusion length of this molybdenum and tantalum varies between 2 to 3 nanometer depending on the heterostructure. So for spin diffusion length less than for interlayer thickness less than the spin diffusion length, this spin angular momentum actually can traverse to the tungsten layer through the interlayer. Hence, we will get a contribution from both the interlayer and the tungsten layer. And however, for very high thickness of the interlayer, the spin angular momentum will be relaxed within the interlayer only, and hence we will see the contribution from the interlayer only, and such that it will seem like there is no tungsten layer there. And we can also see that the saturated value is also different for two different interlayers. We can see that the saturated value is higher for tantalum compared to the molybdenum. This is due to the SOC strength of the different SOC strength of tantalum, which is larger compared to the molybdenum. So, to further strengthen our claim of enhancement in spin pumping with this interlayer, we have performed inverse pinhole effect measurement on a few selected samples, and from the ISHE current at resonance, we can see that for the sample with interlayers, 2 nanometer molybdenum and tantalum, we have got higher ISHE strength, ISHE signal, and even the enhancement in the signal also replicate that we got from FMR measurements. So to conclude my presentation, we have achieved the beta phase of tungsten, which is very crucial for SOT-MRAM application as it possesses high SHA value, and we have achieved a 50% enhancement in damping constant when tungsten layer is placed adjacent to CFA layer, which is further increased to 66 and 75% with 2 nanometer of interlayers of molybdenum and tantalum. So high SOC interlayer with appropriate thickness can enhance the spin current flow through the interface, and which will be very crucial for the practical implementation of SOT based MRAMs. The future perspective or future goal of this work is to study the reciprocal effects through STFR measurements to generalize the concept, and also instead of a single interlayer, if we use multi layers of very low thickness, what will be the effect on spin pumping efficiency. I would like to thank my supervisor, Professor Sujit Chaudhary, and all my lab mates who have helped me in this work. And I also like to thank Professor P.K. Muduli and Himanshu and Pankudi, who have helped us in ISHE measurements, and Professor B.S. Yadav from SSPL DRDO for the SIMS measurement. Thank you, and thank you for your kind of attention. And I would love to answer any of your queries. Thank you.
Thank you, Soumyarup. It's open to the audience. If there are any other questions, please go ahead. Nene, if you want, you can ask your question directly. Or maybe I'll read it from the chat. So he's asking, what about the finite size effect and how it affects the resistivity of beta tantalum at lower thickness regimes? And then he has a second question where he's asking, beta tantalum and interlayer SOC add up. Is both SOC add up in series or parallel?
Okay, first of all, I would like to say what is the finite size effect. So when we, if you see this equation, 1 minute, let me just, yeah. Laser pointer is not working. Okay, when you see this equation, we generally calculate the effective spin mixing conductance, assuming that all the enhancement in damping constant is occurring through spin pumping, which has a 1/T ferromagnetic dependence. However, if there is no, let's say there is no heavy metal or non-magnet, for a single layer ferromagnetic film, there is also a 1/CFA thickness dependency due to its surface interface contribution, or you can say surface to volume ratio. I mean, for a ferromagnetic film with low thickness, there will be a surface scattering because of the high surface to volume ratio. That is what we called a finite size effect due to surface interface scattering. What in my result you can see that for the single layer CFA thin films also with in decrement in the CFA thickness or increment in 1 by CFA, we have observed enhancement in damping constant. And similar enhancement is also found when there is a tungsten layer below the CFA. So if we don't consider this effect, we'll say that all this enhancement is because of the spin pumping, and hence it will lead to a wrong value of G effective or enhanced value, which is not the case. I mean, this is basically to separate out the spin pumping contribution from that contribution that is arising from the ferromagnetic itself. And what is the second question?
So I think is beta tantalum and interlayer SOC are they adding up, and is both SOC add up in series or parallel?
Yes, both SOC are adding up. I series or parallel, I would. I'm not sure about the series parallel stuff, but both SOC are are adding, and that will also depend on the thickness, because if the interlayer thickness is very high, then sorry, the interlayer thickness is very high, then we will not get the contribution. I don't know, my laser point is working.
I can see it. It's visible.
Pointer is working simultaneously. I mean, I'm not doing anything. It's just moving around.
Okay. So, all right, you can just answer the question and we will ignore the pointer. Go ahead.
If the thickness of the tungsten interlayer is very high, there is no contribution or addition, because then the spin angular momentum will be relaxed within the interlayer only. And adding up, if we see adding up, this is added up because of the fact also that both tantalum and tungsten have similar I mean Steinmol angle not magnitude, I would say I mean say both are negative, both have negative spin Hall angle. So yeah.
All right, I'll just take one more quick question from Sachin and then we go to the next presentation. Sachin, please ask your question.
Okay, thank you for the nice talk. So I have the question regarding the transmission coefficient at your CFA and like CFA aluminum, CFA magnesium. So do you consider that in you take that into account for your calculations?
Transmission coefficient. No, all our claim is all based on the variation in damping constant actually, and later we have confirmed it with ISHE measurement of the ISHE signal. So
for example, if I could take you, if I remember well, you have shown that the interfacial roughness is about 0.5 nanometer in your thin films.
0.5 nanometer, yes.
Which don't you think that this is quite large for the spin transmission, like for to scatter the electrons through the interface? Could you comment on that?
There might be some scattering, but it's cannot be like that. All are scattered. All are a part must be transmitted to the heavy metal layer. Okay. And I don't think 0.5 nanometer is a very high value of roughness. I mean, yeah. But all our claim is based on the damping constant enhancement only. Yes.
Thank you.
I have one question.
Yes,
quick. Yeah.
Please go ahead.
I have a very quick question. So, Soumyarup, it's a nice presentation. So, you have shown somewhere like TMS coefficient, that TMS, but I believe that the TMS contribution of TMS is very small in your samples, right?
It's up to 2 to 3% the contribution of TMS. Yeah.
Okay, that's why you have not seen the non-linearity of line width with frequency. So it was not shown in your slides, right?
Actually, I have not shown the line width here.
It's linear. You're fitting the you are
Signal
fitting
was
the
linear. Yes, signal was perfectly linear. Yes.
okay, you are fitting that line width versus frequency with the linear equation, not including the TMS contribution.
No, because there is no nonlinearity was found. I have not shown here,
Okay.
but it was perfectly linear.
Okay, later you are adding the TMS contribution and try to find out the contribution from that. And it's small, right?
Yes.
Okay,
Small,
fine.
I mean negligible.
Yeah, sure. Got it.
All right, thank you, Soumyarup. So we move to our next presentation.